In this paper, we present the first algorithm for the view-independent geometric registration of multiple projectors on a vertically extruded surface. Our method uses an uncalibrated camera and does not require the use of fiduciary markers on the display surface. Furthermore, our method can achieve accurate registration in the presence of large nonlinear distortions such as barrel or pincushion distortion. Such distortions are commonly encountered when using inexpensive short-throw lenses to achieve a compact installation. The key to our method is to impose two practical priors on the display surface, thus reducing the complexity of achieving markerless view-independent registration. First, we assume that our display surface is a vertically extruded surface. Second, we assume that the aspect ratio of the plane formed by the four corners of the display surface has been measured and is known. Our method has three steps. In the first step, we recover both the intrinsic and extrinsic camera parameters. In order to do this, we take a single image of the display surface with the camera and measure the aspect ratio. The camera parameters are estimated using a two-phase nonlinear optimization technique. To provide a reasonable initial estimate of the camera's focal length, we use the focal length value from the EXIF metadata tags embedded in the camera image. In the second step, we recover the 3D shape of the display by reprojecting the top and bottom curves of the display surface in the camera image to 3D using the estimated camera calibration matrix, then intersecting them with the y=0 and y=1 planes. Once we have obtained the 3D shape of the display, we then find a two-dimensional parameterization of its surface. To register the display, we first take a sparse set of correspondences between the projector and the display coordinates. This is done by displaying a sparse grid of blobs which are captured by the camera and then related to the display coordinates using the estimated camera calibration matrix. Finally, to define the mapping between the projector and the display coordinates, we fit a rational Bezier to this sparse set of correspondences. The estimated mapping between the projector and the display can be stored as a per-pixel lookup table to achieve registration in real time on the GPU using a pixel shader. To demonstrate the effectiveness of our method on a general extruded surface, we constructed a display surface from a 4x8 foot sheet of flexible styrene. We attached the sheet to 5 freestanding PVC posts with Velcro. This configuration allowed us to easily change the shape of our extruded display simply by moving any of the posts. We tiled 6 projectors in a 2x3 configuration for the display. Here's an example of an interactive large image viewer running on the display. Here we form a different extruded surface with our screen. Note the accuracy of registration when projecting the difficult case of text. The use of a rational Bezier in our mapping allows us to achieve registration in the face of nonlinear distortions. Here are examples of accurate registration in the face of barrel and pincushion distortions. We also used our method to achieve registration for a 2x4 array of 8 projectors on a cylindrical display, also an extruded surface. We compare our method with chomography-based registration, the only other view-independent registration method currently possible without markers. We also compare our method with one that achieves camera view-dependent registration using a piecewise linear mapping. Note the distortion due to camera perspective. We finally compare the results of a rational Bezier and a piecewise linear mapping between the projector and the display when using sparse correspondences. Our method requires only a sparse sampling of the display to projector correspondences. Note that there is no degradation in the quality of registration when using sparse sampling instead of dense sampling with our method. This enables the use of a low-resolution camera, such as a VGA camera, for registering large display walls made of 8 to 10 projectors. However, such sparse sampling of correspondences yields severe misregistrations when using the piecewise linear method. The piecewise linear mapping can achieve comparable accuracy only when the sampling of correspondences is increased by an order of magnitude. In summary, we presented the first markerless, view-independent registration of multiple projectors on extruded surfaces using an uncalibrated camera. Our method is accurate, efficient, and can be implemented in real time on the GPU.